Zero-knowledge proofs for elliptic curves. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving into one of the most fascinating intersections of cryptography: zero-knowledge proofs applied to elliptic curve cryptography. This presentation will explore how we can prove knowledge of discrete logarithms on elliptic curves without revealing the secret values themselves. Zero-knowledge proofs, or ZKPs, are cryptographic protocols that allow one party, known as the prover, to convince another party, known as the verifier, that a statement is true without revealing any information beyond the validity of that statement itself. This concept might seem paradoxical at first, but it is mathematically rigorous and incredibly powerful. When we combine zero-knowledge proofs with elliptic curve cryptography, we get protocols that are both efficient and secure. Elliptic curves provide a mathematical structure where certain computational problems, like the discrete logarithm problem, are believed to be computationally hard. This hardness assumption is what makes elliptic curve cryptography secure. The discrete logarithm problem on elliptic curves asks, given 2 points p and q on an elliptic curve, where q equals k times p for some scalar k, find the value of k. In standard elliptic curve operations, multiplying a point by a scalar is easy, but finding the scalar given the 2 points is extremely difficult. Zero-knowledge proofs for elliptic curves are used in many modern applications. They are fundamental to privacy-preserving cryptocurrencies like Zcash, which uses zk-SNARKs, zero-knowledge succinct non-interactive arguments of knowledge. They are used in authentication protocols where you want to prove you know a private key without revealing it. They are used in voting systems where you want to prove your vote is valid without revealing who you voted for. They are used in identity systems where you want to prove attributes about yourself without revealing unnecessary personal information. The applications are vast and growing. Throughout this presentation, we'll build from foundational concepts to practical implementations. We'll start by understanding what makes a proof zero-knowledge and what the 3 essential properties are: completeness, soundness, and zero-knowledge. We'll then explore the Schnorr protocol, which is one of the most elegant and widely used zero-knowledge proof systems for discrete logarithms. We'll work through concrete mathematical examples using real elliptic curve parameters, not simplified toy examples. We'll examine how these protocols are implemented in practice, including the role of hash functions in making protocols non-interactive. By the end, you'll understand not just the theory, but how these systems actually work in real cryptographic applications. Foundations of zero-knowledge proofs. Let's establish the foundational concepts of zero-knowledge proofs. A zero-knowledge proof is an interactive protocol between 2 parties: a prover who wants to demonstrate knowledge of some secret information, and a verifier who wants to be convinced that the prover indeed possesses this knowledge. The remarkable property of zero-knowledge proofs is that the verifier learns absolutely nothing about the secret itself, only that the prover knows it. This is not just security through obscurity or hiding information temporarily. It's a mathematical guarantee that no computational power, even unlimited, can extract the secret from the protocol transcript. Every zero-knowledge proof must satisfy 3 fundamental properties. The first is completeness, which means that if the prover is honest and actually knows the secret, the verifier will always be convinced. An honest prover will always succeed in convincing an honest verifier. This is essential because a proof system that rejects valid proofs is useless. The second is soundness, which means that if the prover does not know the secret, they cannot convince the verifier except with negligible probability. A cheating prover who does not actually know the secret has essentially no chance of fooling the verifier. The probability of a successful cheat is typically something like 2 to the negative 100, which is astronomically small. The third is zero-knowledge, which means that the verifier learns nothing about the secret beyond the fact that the prover knows it. Even if the verifier records the entire protocol execution and tries to analyze it later with unlimited computational resources, they cannot extract any information about the secret. The zero-knowledge property is often demonstrated through the concept of a simulator. If a simulator algorithm can produce transcripts of the protocol that are indistinguishable from real protocol executions, even without knowing the secret, then we've proven the protocol is zero-knowledge. The logic is, if fake transcripts look exactly like real transcripts, then real transcripts cannot contain any information about the secret. This is because the fake ones certainly don't contain any such information, since the simulator never had the secret to begin with. There are different flavors of zero-knowledge proofs. Interactive zero-knowledge proofs require back-and-forth communication between the prover and verifier. The verifier sends random challenges, and the prover responds to these challenges. Non-interactive zero-knowledge proofs, or NIZKs, eliminate the interaction by using cryptographic hash functions to generate challenges deterministically. This is done through the Fiat-Shamir heuristic, which we will discuss later. Non-interactive proofs are particularly useful in blockchain and distributed systems where you can't have real-time interaction between parties. Another important distinction is between computational zero-knowledge and statistical or perfect zero-knowledge. Computational zero-knowledge means that no efficient algorithm can extract information from the protocol, but a computationally unbounded adversary theoretically could. Statistical zero-knowledge means that even with unlimited computational power, the adversary has only a negligible chance of extracting information. Perfect zero-knowledge means it's information theoretically impossible to extract anything, even with infinite computational power. Most practical systems, including the elliptic curve protocols we'll discuss, provide computational zero-knowledge, which is sufficient for real-world security. Elliptic curve discrete logarithm problem. To understand zero-knowledge proofs on elliptic curves, we first need to understand the underlying hard problem that provides security. The elliptic curve discrete logarithm problem, or ECDLP. An elliptic curve is defined by an equation of the form y squared equals x cubed plus a times x plus b. All computed modulo some prime number page points on this curve form a mathematical group under a special addition operation. The group has a special element called the identity or point at infinity, which serves as the additive identity. In elliptic curve cryptography, we start with a base point g on the curve. This base point has a certain order n, which means that if you add g to itself n times, you get back to the identity point. The order n is typically a large prime number, often 256 bits or more. When we multiply the base point g by a scalar k, written as k times g or using the notation k multiplied by g, we mean adding g to itself k times. This is called scalar multiplication, and it's the fundamental operation in elliptic curve cryptography. Here's the key security assumption. Given a base point g and a public point q where q equals k times g for some secret scalar k, finding the value of k is computationally infeasible. The scalar multiplication operation is easy to compute in the forward direction. You can compute q equals k times g efficiently using algorithms like double and add. But going backwards, recovering k from q and g, is believed to be extremely difficult. The best known algorithms for solving ECDLP have exponential time complexity, requiring approximately square root of n operations, where n is the order of the base point. For a 256-bit curve, this means roughly 2 to the power of 128 operations, which is far beyond the reach of any conceivable computer. Let's work with a concrete example using the SEC-P256K1 curve, which is used in Bitcoin and Ethereum. The SEC-P256K1 curve has the equation y squared equals x cubed plus 7, computed modulo a very large prime page. The base point g has coordinates that are specific 256-bit values, and the order n is approximately 2 to the power of 256. In practice, a private key in SEC-P256K1 is just a random integer k between 1 and n-1. The corresponding public key is the point Q equals K times G. The security of the system relies on the fact that even though everyone can see Q and everyone knows G, nobody can figure out K. The discrete logarithm problem is what makes elliptic curve cryptography useful for digital signatures, key exchange, and encryption. It's also what makes zero-knowledge proofs possible on elliptic curves. In a zero-knowledge proof of knowledge of discrete logarithm, the prover wants to convince the verifier that they know the value K such that Q equals K times G, without revealing K itself. This is exactly what we need for many cryptographic protocols. For example, in authentication, you want to prove you know the private key corresponding to a public key, without revealing the private key. In ring signatures, you want to prove that you know a private key corresponding to one of several public keys, without revealing which one. Zero-knowledge proofs give us the mathematical tools to accomplish these goals. The Schnorr Protocol Overview. The Schnorr Identification Protocol is one of the most elegant and widely used zero-knowledge proof systems for proving knowledge of discrete logarithms on elliptic curves. It was invented by Klaus Schnorr in the late 1980s and has become a fundamental building block in modern cryptography. The protocol allows a prover to convince a verifier that they know a secret scalar K such that Q equals K times G, where G is the base point and Q is the public key, without revealing any information about K. The beauty of the Schnorr protocol lies in its simplicity and elegance. It consists of 3 moves, which cryptographers call a sigma protocol. The first move is commitment, where the prover chooses a random value and commits to it by sending a related value to the verifier. The second move is challenge, where the verifier sends a random challenge to the prover. The third move is response, where the prover uses their secret knowledge to compute a response that depends on both the commitment and the challenge. The verifier then checks whether the response satisfies a specific verification equation. Let's outline the protocol step by step. Setup. The prover knows a secret scalar K, and everyone knows the corresponding public point Q equals K times G. The prover wants to prove knowledge of K without revealing it. Step 1. Commitment. The prover generates a random scalar R, called the nonce. This must be chosen uniformly at random from the range of valid scalars. The prover computes the commitment R equals R times G and sends R to the verifier. This commitment locks in the prover's choice of R without revealing it. Step 2. Challenge. The verifier generates a random challenge scalar E and sends it to the prover. This challenge should be chosen uniformly at random to prevent the prover from predicting it. Step 3. Response. The prover computes the response S equals R plus E times K, where all arithmetic is done modulo the curve order n. The prover sends S to the verifier. Step 4. Verification. The verifier checks whether S times G equals R plus E times Q. If this equation holds, the verifier accepts the proof. Otherwise, they reject it. Why does this protocol work? Let's verify the verification equation. We know that Q equals K times G, so E times Q equals E times K times G. We know that R equals R times G. The response is S equals R plus E times K. Therefore, S times G equals the quantity R plus E times K times G, which equals R times G plus E times K times G, which equals R plus E times Q. So, if the prover computed S correctly, the verification equation will hold. An honest prover who knows K will always be able to compute the correct response, so the protocol satisfies completeness. The protocol also satisfies soundness. If a prover doesn't know K, they cannot predict the verifier's challenge E. To cheat, they would need to either predict E before committing to R, or they would need to solve for K given the verification equation. But predicting E is impossible if it's chosen randomly, and solving for K would require breaking the discrete logarithm problem. The probability of a cheater succeeding is essentially the probability of guessing E, which for a 256-bit challenge is approximately 2 to the negative 256, utterly negligible. The protocol is also zero-knowledge, which we can show by constructing a simulator that produces indistinguishable transcripts without knowing K, but we'll explore that in more detail later. Schnorr protocol mathematical example. Let's work through a complete mathematical example of the Schnorr protocol using actual elliptic curve parameters. We'll use simplified numbers that are much smaller than real cryptographic parameters, but the mathematics is identical. This will help you understand exactly how the protocol works in practice. Imagine we're working with an elliptic curve where the base point g has order n equals 29. This means that 29 times g equals the identity point. In reality, n would be a 256-bit prime, but 29 is easier to work with for illustration. Setup phase. The prover has a secret private key k equals 7. They compute their public key q equals 7 times g. Everyone knows g and q, but only the prover knows k equals 7. The prover wants to prove they know k without revealing it. Now we begin the protocol execution. Commitment phase. The prover generates a random nonce r equals 13. This must be chosen uniformly at random and must never be reused. The prover computes the commitment r equals 13 times g. The prover sends r to the verifier. At this point, the verifier sees r but has no information about rk. The commitment r is like a sealed envelope. It commits the prover to their choice of r without revealing it. Challenge phase. The verifier generates a random challenge e equals 5. In practice, the verifier would choose e uniformly at random from the range 0 to n-1. The verifier sends e equals 5 to the prover. The randomness of this challenge is crucial for security. If the prover could predict or influence e, they might be able to cheat. Response phase. Now the prover uses their secret knowledge to compute the response. They calculate s equals ar plus ee times k, all modulo n. Substituting our values. S equals 13 plus 5 times 7, modulo 29. Let's compute this. 5 times 7 equals 35. So S equals 13 plus 35, which equals 48. Now we reduce modulo 29 to 48. Modulo 29 equals 19, because 48 minus 29 equals 19. Therefore S equals 19. The prover sends S equals 19 to the verifier. In the verification phase, the verifier checks the verification equation. S times G equals R plus E times Q. Let's verify this. For the left side, S times G equals 19 times G. Now, for the right side, R plus E times Q equals R plus 5 times Q. We know that Q equals 7 times G. Therefore, 5 times Q equals 5 times 7 times G, which gives us 35 times G. Since we are working modulo 29, 35 times G equals 6 times G, because 35 modulo 29 is 6. So, the right side becomes R plus 6 times G. We know that R equals 13 times G. Therefore, the right side equals 13 times G plus 6 times G, which totals 19 times G. Both sides now equal 19 times G. Thus, the equation holds, and the verifier accepts the proof. This example demonstrates several key points. First, the prover never revealed K equals 7, yet they successfully convinced the verifier. Second, the response S equals 19 does not directly reveal R or K. It is a combination of both. Third, the verification equation holds precisely because of the mathematical structure of the protocol. Fourth, the random challenge E is essential. Without it, a malicious prover might be able to forge proofs. In real implementations with 256-bit numbers, the mathematics is identical, but the security is much stronger because the space of possible values is astronomically larger. Zero-knowledge property of Schnorr. Now let's examine why the Schnorr protocol is truly zero-knowledge. The definition of zero-knowledge requires that the verifier learns nothing about the secret K beyond the fact that the prover knows it. To prove this, we use a technique called simulation. The idea is to show that we can create fake protocol transcripts that look exactly like the real ones, without ever knowing the secret K. If these fake transcripts are indistinguishable from real ones, then the real transcripts cannot contain information about K. This is because the fake transcripts definitely do not contain such information, since the simulator never had access to K. Here's how we construct a simulator for the Schnorr protocol. The simulator's goal is to produce a transcript consisting of commitment R, challenge E, and response S, that passes the verification equation S times G equals R plus E times Q, without knowing K. Remember, in a real protocol execution, the prover knows K, but our simulator does not. Yet it must produce a valid-looking transcript. The simulator works as follows. First, the simulator chooses a random challenge E in the real protocol. The verifier chooses E, but the simulator gets to choose it because we are creating a simulation. Second, the simulator chooses a random response S again. In the real protocol, S is computed from R, E, and K, but the simulator just picks it randomly. Third, the simulator computes R equals S times G minus E times Q. This is the clever part. In the real protocol, we compute S from R, E, and K in the simulation. We compute R from S and E. Let us verify this works. If R equals S times G minus E times Q, then R plus E times Q equals S times G minus E times Q plus E times Q equals S times G, so the verification equation holds. The simulated transcript consists of R, E, and S, and it passes verification. Moreover, if E and S are chosen uniformly at random, then R is also uniformly distributed over all possible commitment values. The key insight is that the simulated transcript has exactly the same probability distribution as a real transcript. In both cases, E is uniformly random. S is uniformly random. In the real protocol, S equals R plus E times K, where R is uniformly random, and this makes S also uniformly random, and R is determined by the verification equation. Since we cannot distinguish simulated transcripts from real transcripts, the real transcripts must not contain any information about K. This simulation argument is powerful because it works even against computationally unbounded adversaries. Even if you had infinite computational power and could analyze the transcript forever, you couldn't extract K, because you couldn't even tell whether the transcript was real or simulated. This is what we mean when we say the protocol is zero knowledge. There is an important caveat. The simulation works only if the challenge E is chosen randomly by the verifier after seeing the commitment R. If the prover could choose E or know it in advance, the protocol would not be sound. If the verifier could choose E after seeing both R and S, the protocol would not be zero knowledge. The specific order of operations, commitment, then challenge, then response, is essential for both soundness and zero knowledge. This three-move structure is why we call it a sigma protocol. Fiat-Shamir heuristic transform. The Schnorr protocol as we've described it is interactive. It requires the prover and verifier to communicate back and forth. The prover sends a commitment, the verifier sends a challenge, and the prover sends a response. This interaction is fine for some applications, like real-time authentication, but it's problematic for others. In blockchain systems, you can't have interactive protocols because there's no real-time communication between the signer and the verifiers. In digital signature schemes, you want to create a signature once and have anyone be able to verify it later, which requires non-interactivity. This is where the Fiat-Shamir heuristic comes in. The Fiat-Shamir heuristic is a technique for converting interactive zero-knowledge proofs into non-interactive ones. The key idea is to replace the verifier's random challenge with the output of a cryptographic hash function. Instead of having the verifier send a random challenge E, the prover computes E themselves by hashing the commitment along with any other relevant public information. The hash function acts as a random oracle, producing unpredictable outputs that the prover cannot control or predict before creating the commitment. Here is how we apply Fiat-Shamir to the Schnorr protocol. Setup remains the same. The prover knows secret K, and everyone knows public key Q equals K times G. Step 1. Commitment. The prover generates a random nonce arranged by and computes commitment arranged by equals arranged by times G. Step 2. Challenge generation. Instead of receiving EE from the verifier, the prover computes EE equals the hash of arranged by concatenated with Q concatenated with any additional context. The hash function is typically SHA-256 or SHA-3, and its output is interpreted as an integer modulo the curve order n. Step 3. Response. The prover computes S equals arranged by plus EE times K, modulo n, exactly as before. The proof consists of the pair arranged by and S. Step 4. Verification. Anyone can verify by computing EE equals the hash of arranged by concatenated with Q, then checking whether S times G equals arranged by plus EE times Q. The Fiat-Shamir transform turns our interactive protocol into a signature scheme. The proof R&S is essentially a signature on the message, which could be empty or an actual message being signed. This is exactly how Schnorr signatures work. A Schnorr signature on a message M consists of R and S, where E equals hash of R concatenated with Q concatenated with M. The security relies on the hash function behaving like a random oracle, meaning its outputs are unpredictable and uniformly distributed. In the random oracle model, where hash functions are idealized as truly random, the Fiat-Shamir transform preserves the security properties of the interactive protocol. The resulting non-interactive proof has the same soundness and zero-knowledge properties as the interactive version. However, we must be careful about the hash function choice. In practice, we use cryptographic hash functions like SHA-256, which are not truly random but are designed to be cryptographically secure. The random oracle model is a theoretical idealization, and there are subtle attacks that work against some implementations in the real world, though Schnorr signatures with proper hash functions remain secure. The Fiat-Shamir heuristic is not just useful for Schnorr, it is a general technique for making any public coin interactive protocol non-interactive. Public coin means the verifier's messages are just random coins. They do not depend on the prover's messages except for their timing. Most zero-knowledge proofs, including zk-SNARKs and zk-SNARKs, use Fiat-Shamir or similar techniques to achieve non-interactivity. It is one of the most important tools in the modern cryptographer's toolkit. Schnorr signatures implementation. Let's examine how Schnorr signatures are implemented in practice, using real elliptic curve parameters and actual code considerations. Schnorr signatures are now standardized in Bitcoin through BIP 340, which specifies exactly how to implement them securely on the ZKP256K1 curve. The implementation details matter tremendously. Small mistakes can completely break security. The signature generation process works as follows. Input: a message M to be signed, a private key K between 1 and n-1, and the corresponding public key Q equals K times G. Step 1. Nonce generation. Generate a random 256-bit integer R. This must be generated using a cryptographically secure random number generator. The security of the entire signature depends on the randomness and uniqueness of R. If R is predictable or if the same R is used twice with the same private key, the private key can be completely recovered. This is not a theoretical attack. It has happened in practice, most famously in the PlayStation 3 signing key compromise and in some Bitcoin wallet implementations. Step 2. Commitment. Compute R equals R times G if the Y coordinate of R is odd, as specified in Bitcoin's BIP 340. Negate R to make it even. This optimization reduces signature size. Step 3. Challenge. Compute E equals hash of Rx coordinate concatenated with Qx coordinate concatenated with MBIP 340 uses a specific hash function called tagged SHA-256, which includes a tag in the hash to prevent cross-protocol attacks. Step 4. Response. Compute S equals R plus E times K, modulo N. The signature is the pair consisting of the X coordinate of R and the value S. In BIP 340, This gives a 64-byte signature. 32 bytes for Rx coordinate, 32 bytes for S. The verification process is straightforward. The inputs are a message M, a signature consisting of the Rx coordinate and S, and a public key Q. For step 1, parsing. Interpret the Rx coordinate as an integer and reconstruct point AR by finding the corresponding Y coordinate on the curve. By convention, choose the even Y coordinate. For step 2, the challenge. Compute EE equals the hash of the Rx coordinate concatenated with the Qx coordinate concatenated with M, using the same hash function as in signing. For step 3, verification. Compute P equals S times G minus EE times Q. Check whether P equals AR. If so, accept the signature. Otherwise, reject. Let's verify the verification equation. We have S equals R plus E times K, therefore, S times G equals R times G plus E times K times G. This simplifies to R plus E times Q, rearranging. S times G minus E times Q equals R, so we compute P equals S times G minus E times Q, and check if P equals R. This is mathematically equivalent to the verification equation we used earlier. S times G equals R plus E times Q, just rearrange. Implementation considerations are critical. First, nonce generation must use a cryptographically secure random number generator. The system random number generator or a hardware random number generator should be used, never a predictable pseudo-random generator. Second, nonce uniqueness must be guaranteed. Some implementations use deterministic nonce generation based on RFC 6979, which generates AR as a deterministic function of the private key and message. This eliminates randomness-related failures but requires careful implementation. Third, all scalar arithmetic must be done modulo n, the curve order. Integer overflow or reduction errors can leak information. Fourth, timing attacks must be prevented. Scalar multiplication and other operations should be implemented in constant time, meaning the execution time does not depend on the secret values. Fifth, memory must be securely cleared. After computing S, the values AR and intermediate results should be zeroed from memory to prevent them from being recovered later. Schnorr signatures have several advantages over ECDSA, the digital signature algorithm traditionally used in Bitcoin and Ethereum. Schnorr signatures are simpler to implement correctly. They have a security proof in the random oracle model, while ECDSA's security proof requires additional assumptions. Schnorr signatures support key aggregation, allowing multiple parties to create a single signature on a shared public key, which is useful for multi-signature schemes. Schnorr signatures are slightly smaller and faster to verify. For these reasons, Bitcoin added Schnorr signature support in 2021, and they are increasingly used in modern cryptographic systems. Ring signatures and anonymity. One of the most powerful applications of zero-knowledge proofs on elliptic curves is ring signatures. A ring signature allows a signer to prove they know the private key corresponding to one public key in a set of public keys, without revealing which one. This provides anonymity within a group. The verifier knows the signature came from someone in the group, but cannot determine who. Ring signatures are fundamental to privacy-preserving cryptocurrencies like Monero and are used in various anonymous credential systems. The concept of a ring signature can be understood through an analogy. Imagine a group of government officials, each with a private key. One of them wants to leak a document in a way that proves it came from someone in the group, but without revealing which official it was. They create a ring signature using all the officials' public keys. The signature proves that someone who knows one of the private keys created it, but doesn't reveal which private key was used. This gives plausible deniability while still authenticating the source as coming from the authorized group. Let's examine how ring signatures work mathematically. Suppose we have a ring of n public keys, Q1, Q2, up to Qn, where each Qi equals Ki times G. For some private key Ki, one signer knows one of these private keys, say Kj, and wants to create a signature that could have been created by any member of the ring. The challenge is to construct a proof that convinces the verifier that the signer knows one of the discrete logarithms, without revealing which one. The most common ring signature construction is based on the Schnorr protocol, extended to handle multiple public keys. Here is a simplified version. In step 1, the signer chooses random nonces for all positions except their own position j. For each I not equal to j, the signer chooses random Ri and Si. For their own position j, the signer chooses random Rj. In step 2, commitments are computed. For positions I not equal to j, compute Ri equals Si times g minus hash I times Qi, where hash I is some challenge value the signer chooses. For position j, compute Rj equals Rj times g. In step 3, a ring hash is computed. E equals the hash of all Ri values concatenated with all Qi values concatenated with the message M. In step 4, the challenge for position j is computed. Ej equals E minus the sum of all other Ei values. In step 5, the response for position j is computed. Sj equals Rj plus Ej times Kj. The signature consists of all the Ri values and all the Si values, plus the ring hash E. Verification works as follows. The verifier reconstructs the challenges. Compute Ei for each position using the signature values. Then verify that the sum of all Ei equals the ring hash E. Also verify that the ring equation closes. For each position I, check that Si times G minus Ei times Qi equals Ri. If all checks pass, the signature is valid. The key insight is that the signer can freely choose the challenges and responses for all positions except their own. For their own position, they must compute the response honestly using their secret key. But from the verifier's perspective, all positions look symmetric. There's no way to tell which one corresponds to the real signer. Ring signatures provide strong anonymity guarantees. Even if an adversary knows all the private keys except one, they still cannot determine who the real signer was. The anonymity set size is exactly the ring size. If there are 100 public keys in the ring, the signer has 1 in 100 anonymity. Larger rings provide better anonymity but result in larger signatures. In Monero, ring signatures typically include 11 public keys, providing 1 in 11 anonymity for each transaction. Combined with other privacy techniques like stealth addresses and confidential transactions, this provides strong privacy for cryptocurrency users. Advanced ZKP constructions and applications. Beyond basic Schnorr proofs and ring signatures, there are many advanced zero-knowledge proof constructions for elliptic curves that enable sophisticated applications. These include proofs of representation, proofs of range, proofs of set membership, and various forms of succinct non-interactive arguments. Let's explore some of these advanced constructions and their real-world applications. Proofs of representation allow proving knowledge of multiple discrete logarithms simultaneously. For example, proving knowledge of scalars k1 and k2 such that q equals k1 times g1 plus k2 times g2, where g1 and g2 are different base points. This is useful in commitment schemes where you commit to a value using randomness, and later want to prove properties about the committed value without revealing it. The Peterson commitment scheme works this way. To commit to value v with randomness r, compute c equals v times g plus r times h, where h is another base point. You can later prove statements about v without revealing v or r. Range proofs demonstrate that a committed value lies within a specific range. For example, they can prove a transaction amount is between 0 and 2 to the power of 64 minus 1, without revealing the actual amount. This is crucial for confidential transactions where you want to hide transaction amounts, while still proving that the amounts are valid. This means they are non-negative and do not overflow. Bulletproofs are a particularly efficient type of range proof that use elliptic curve commitments. A bulletproof's range proof for a 64-bit value is only about 650 bytes, and it can be verified efficiently. Multiple range proofs can be batched together for even better efficiency. Set membership proofs allow you to prove that a committed value is one of a specific set of values, without revealing which one. For example, proving that your age is in the set 18, 19, 20, 21 without revealing your exact age. Or proving that your account balance is above a threshold by proving it is in the set of all values above that threshold. These proofs use techniques similar to ring signatures, but are more flexible and can handle larger sets more efficiently. zk-SNARKs, zero-knowledge succinct non-interactive arguments of knowledge, are a powerful class of proofs that can prove arbitrary computational statements. They allow proving statements such as, I know a secret input x such that some complex function f of x equals a public output y. The proof is succinct, meaning very small, typically a few hundred bytes, regardless of the complexity of f. The proof is non-interactive and can be verified very quickly. zk-SNARKs used in systems like Zcash use elliptic curve pairings, which are bilinear maps between elliptic curve groups. The mathematics is quite complex, involving concepts like quadratic arithmetic programs and polynomial commitment schemes. The applications of these advanced ZKP constructions are numerous and continuing to grow. For example, in cryptocurrencies, they enable privacy-preserving transactions where the amounts and parties involved are hidden. In identity systems, they allow for selective disclosure. This means you can prove attributes about yourself, such as proving you are over 18, without revealing unnecessary information like your exact birth date. When it comes to voting systems, they facilitate verifiable voting, enabling you to prove your vote was counted accurately without disclosing who you voted for. Within supply chain systems, these constructions allow for the verification of properties about goods without revealing confidential business information. And in cloud computing, they support verifiable computation, letting you prove that a computation was performed correctly without the need to rerun it. The field of zero-knowledge proofs is rapidly evolving. New constructions like zk-SNARKs offer transparency, meaning no trusted setup, and post-quantum security. New applications are being discovered constantly. As cryptography continues to advance, zero-knowledge proofs on elliptic curves will play an increasingly important role in building secure, private, and verifiable systems. The mathematical foundations we've covered in this presentation, the discrete logarithm problem, the Schnorr protocol, and the Fiat-Shamir heuristic, remain central to understanding and implementing these advanced systems. Thank you for your attendance. Please consider subscribing to the channel.